Hello, everyone, and welcome to Handmade Hero, where we code a complete game live on stream. We left off at a rather enticing location yesterday, or I should say last weekend. It's yesterday in stream time, but it's last weekend in the real-time world. We now have some pretty great ray tracing times compared to what we used to have. And actually much better quality results, too. I don't know, although I'll tell you right now, that is not what I wanted to see. I don't remember exactly where we left off, but we were doing lighting testing. I think we turned off the actual casting and took a time time sample at the end of last stream, so we're going to have to turn the Raycaster back on first before we do that. I believe we just turn the cost metric to 0 when we're actually doing that test. So at the top of grid Raycast, we usually set cost metric to 0. So this line right here. But if we turn it back on, it's in really good shape. The speed is quite good, and the quality is actually better than the old one. So as far as the Raycaster, I think we're getting pretty close to done, but there's a couple things I think we can do that would improve the speed of it dramatically. Now, one of the things that we have to look at now is we were taking some timings in just the standalone, let's take a look at how fast this routine can run profile part of things. And what you can see here is that if we start looking at how long the bookends take, which is to say without actually doing any ray tracing, just doing setup work and then the cooldown work, basically the two things that have to happen on either side of the ray tracing, which is at startup we have to do some builds, right? We have to get some spatial structures ready for our grid walk. And then on exit, we have to do a bunch of stuff. There's two basic phases. One phase is we have to write out the actual color data to sum it into the textures that we're going to download to the GPU. And then the other thing we have to do is we have to blur the spec map into the diffuse map. So those two processes are, taking a lot of time right now. You can see that what we've got it down to 5.1 seconds for our stress test. That's down from 7.4. And we know that even if we weren't ray tracing at all, it's 2.5, right? So only half our time is now currently spent in the ray tracer. So what that means is that really we want to look at this number as if this number is really itself minus the 2.5. So it's really and this is rounded up, it's 2.6. So really this number is more like 2.5. That's what we're actually looking at for the time that the actual ray tracing takes. And then the other stuff, so stuff that supports the ray tracer and building the maps at the end, that's the other half of the time. Now that's both good and bad. It means that our ray tracer is getting very fast because now it's starting to be actually not even the hotspot. It's starting to drop below the 50% line. So good on us for that. But it also means that, we're going to have to start going and looking at the other pieces of the code and optimizing them. But that's okay because we knew sort of we had to do that. And also, this is how optimization works. The faster you make one part and the more you focus on one part, the slower everything else gets by comparison because that thing keeps getting faster and the other things stay the same speed. So we did an optimized compute irradiance, and we know that really dropped the time dramatically. And we know that that's the case because... Whoa. Wow. Haven't seen 4Coder crash in a very long time, and all I was doing was looking at I wonder what's going on here. It must be bad RAM. This is an ancient version of 4Coder that I'm using. I just never have any time anymore. I'm always so busy with everything that I don't ever have any time to actually update my forecoder. But one of these days, I will update the stream forecoder to something. I was going to switch to Ryan Fleury's custom layer and just backport my changes into it. That way there was like a public repository of it. It's been long overdue, but we'll have to just dedicate a stream or two to doing that. Anyway, what I was trying to say was, if you take a look at what all this entails, basically in that remaining 2.5 seconds that we know is being taken up by the actual meat of the ray tracer, we haven't taken a sample yet to see how fast it would be if the grid ray tracer were running with the fastest possible irradiance computations. So if we were, for example, to take compute voxel irradiance at and try to reduce the total runtime of it to something even less, like we did optimization of it, as you can see here, to sort of simplify things a bit. But the question is, like, can we take a sample that sort of gets rid of some of this? And also, like, we don't know very much about this. We haven't looked at get octahedral offset at all. But if you take a look at how this is working here, it's entirely possible that this would flow much more cleanly if this were done in float as well, SSE as well, right? Because you can see there's actually two fairly large parts to this. There's the get octahedral offset part, and then there's the octahedral from unit vector part. So it's actually got to do both of these things, and both of these things could be they could be being done very stupidly by the compiler, right? So we probably need to take this and make this more sane as well, because we want this whole routine to flow as smoothly as possible. And especially when you start seeing things like sign of and absolute value, it's always possible that those things are not implemented very cleanly when the compiler has to look at them and figure out that what's being done can be... Yeah, I mean, like... So, especially when you see this, like, that's just not... You probably never want that, right? Now, we don't really know, like, maybe the compiler's doing something smart there, so we could look at the disassembly and see. But based on what we saw before, if I had to guess right now, before we look at the disassembly, I would say, we're probably in a lot of trouble there. Because FABS F is... like maybe going to be done with an AND, but maybe it's not. I mean, I don't know. I don't know what it's going to produce. In fact, let's just find out. So if I go ahead and take a look at this, I don't know if it welds the voxel irradiance sampler directly into this routine. It should, but I don't know if it does. Actually, sorry, compute voxel irradiance at. So it doesn't, because here we are. And you can see us calling from here. And what I want to do in here is I just want to take a look mainly at this. And maybe now would be a good time to sort of get this over on the other side here, because we maybe just want to be able to see it a bit larger. And at the moment, I'm not really looking particularly hard at the state. Like, I'm not trying to debug this assembly code, so I don't really need a watch window right now. Mostly all I'm looking at here, and you know what? Why do I still have code bytes on? We don't really need code bytes at the moment. It just makes it a little harder to read. You know what? Here's a random remedy request. I always throw these out on stream. I feel bad for George, because I'm just like, it would be cool if unicorns could fly. But like, if you look at this, it's pretty hard to read because it's kind of just unformatted, right? And it would be kind of cool if this could be tabulated a little bit. Like, if there was another one of these checkboxes that was like align columns or something, and you could see the assembly language code. So these would all of the params would line, like all of the arguments would line up here. So MoveSD would have the XMM0 be in the same place as like the MOV, even though they're different length mnemonics, right? Something like that would probably be pretty cool. And, I don't know. There's probably just a couple simple things you could do to make that kind of readable. Another example would be like, suppose you color highlighted these somehow, so everywhere that XMM1 was used, it was a specific color, or you could just click on it anyways, and if whatever you clicked on, that one at least would highlight, so you could see like, this is moving into XMM1, and I'm kind of wondering like where that's used, so it would then highlight the next place that XMM1 was used, happens to be here. But if it was like lower down, it might take you a little while to find that, right, when you're just blind reading some assembly from the compiler. If it's your own code, you usually don't need this, but when you're looking at the code that the compiler generates, which is most often what you're looking at, because it's pretty rare these days to really write routines in assembly, you're not going to have a whole lot of them. So a lot of times when you're looking at the assembly language, you're looking at assembly language that wasn't yours. And so it would be kind of cool to have a little bit more in here. It doesn't have to be nuts, because this is not a reverse engineering tool. You see those tools that are like designed for reverse engineering, and then there's like all these crazy things like, let me mark up what this one is, and let me replace this use of XML with an actual name so I can see it. That stuff, it would just be a waste of your time, because nobody who's just casually inspecting compiler code like you would in a debugger like this is going to use any of those features, so they'd just be wasted. But just a slightly better view of it here would be cool, because that would allow you to read it a little bit more easily. So just features that allow you to read the code a little bit more easily, not really reverse engineer it, but just read it, seem like they would be worth it. I don't know, just throwing that out there. So anyway, if we take a look at this code here, I'll be honest, I don't even think I know that instruction. That's probably sort of embarrassing for me to say, but I honestly just don't even remember if I've ever used that. So let's find out, because I do not know what that is. It's a single scalar of some kind, but I have no idea what that does. Let's see. So it is a pretty simple instruction. It's a port 0 only, and it's a 1 throughput, 1 UOP. So it's only on port 0, and it's 1 cycle long. Seems pretty straightforward. I don't know if the intrinsics guide will have that in it. We can look, because I may have to look in the architecture manual, but I assume this is probably in here. So that's just the compare. That's just the compare. So interestingly, like, what's the... okay. Oh, wow. Okay. So I feel kind of dumb. I never knew this. I guess it's because when I write SSE code, I pretty much always am running it wide. So I've actually never encountered this instruction, which I know is kind of crazy. Yeah, I feel like that was worth doing, because, it's just kind of dumb that I didn't know that. This is kind of the nature of modern programming. When you have so much stuff to do, you don't have a chance to really get as into it as you would like. So normally, I always use the comp instructions. And what you can see here is they have a special one just for if you're only doing a single scalar. And what it looks like it does is it actually does the comparison of just the low order float. And it puts it right into the flags, I assume. This says, this says return the Boolean result, but that's because they're talking about the intrinsic. But there is no such thing as return the result, right? I mean, this is an instruction, so it does something with the result. And if you're talking about something that doesn't take a register as a destination, because it doesn't here, you can see that the only other register would be this one. And so if it's just doing one Boolean result, that's going into the flags. So that means you can do this and then do a jump. I didn't know that because I always do wide when I'm writing SIMD, because the whole point of running SIMD is usually doing wide. I never really think about what the instruction patterns are going to be for single float. But of course, single float happens all the time. Anytime you're compiling code that's just type the word float. So this right here is presumably an instruction that they're basically saying, look, we're going to compare these two, probably because it's like this. Where did it go? Octahedral from Univit. Here we go. Probably because of this. Like, again, it's hard to see exactly what's doing here because I haven't followed through the code and it's really not marked up. Here, it's hard to tell where it came from. But if you take a look at what's going on here, it's probably doing like this test or something and trying to jump around it, right? That's the charitable interpretation. The fact that I see multiple ones of these makes me a little nervous. It could be that those are there for a reason, and the fact that there's only two. So what's the second one, though? There's not really going to be an if in here, right, folks? So is it back in here? So I'm not super comfortable with that. I don't really know what that's doing, right? So that's a little bit scary. Because I can't really work out. I'd have to start stepping through this and really pay attention to what it's doing, but I don't really understand why we should be seeing two of those, because if it was doing a branch, I'm not sure what the other one was. We're not really doing any other branches in here, right? You could kind of see like there really isn't anything else where anyone should be doing any kind of branch. All the rest of these, as far as I know, are just straight line code. So that's a little disquieting. And again, that just makes me nervous because I don't know why the compiler would think that it needed to do two tests like that, because there really aren't two things to test. So let's just double check. Let's see what's going on there. I'm going to go to floor here, but this is a straight line piece of code, right? It's not a test. Hadamard product v2, floor, those are all obviously, not going to do branches unless the compiler did something really crazy. So octahedral, oh, no, never mind. Sorry, I just jumped to the wrong function. So looking at this, the absolute value here, there's 3 of them, so I would have expected to see 3 of these if it was somehow interpreting that as a branch, but it doesn't, that just, oh, there they are, 1, 2, 3. I just missed the third one. So you can see 3 distinct calls to that. I'm not sure where the actual other branch would be at that point, meaning the branch that does VZ less than 0. I'm not sure where that is, right? So I don't know if the compiler did something smarter there, or if I'm just missing one of these. So there's 3. So I'm not seeing... So I'm not seeing much else. So I don't know why I'm not seeing 4 of them. I mean, one reason might be, so here's the thought. Like, it could be that the reason that I'm not seeing 4 of them is because this test is the same as that test. So what it may have done is just welded those 2 pieces of code together. You know what I'm saying? In other words, when you saw absolute value, if absolute value was being done stupidly, which it may well have been, I don't know, that, you know, it could be saying like, okay, let's do a test on this to see if it was less than 0. You know, I really don't know. So I think what I would prefer to do here is just make this not as stupid. So if we take a look at what's going on with absolute value, I'm pretty sure we've already done this, right? And you can see here that this is how you would prefer to do absolute value. So you basically just say, look, we know the sign bit is the highest bit of each lane. So if we just load in, you know, into the register, a thing with the high bit set and everything else clear, then we should just be able to mask off that part, right? Now, if you take a look at how this is written, I don't know that this is particularly smart. I suppose it depends exactly how the compiler wants to generate this. It probably will just put this and load it. I mean, I don't really know. But let's suppose you were actually going to generate it for real. You know, this is probably not the fastest way you would want to do this. So, for example, if you wanted to, you could just get rid of this not and make this an and not, right? Because we're knotting this, and there really was no reason that we had to knot it because there's an instruction that knots it for you. So if the compiler actually thought that it needed to do that specifically, you know, not so good. And in fact, you know, we could just say, all right, look, let's see what's going to happen on the compiler we're using here. If I go to Godbolt, and yeah, we don't need a privacy policy because I'm streaming this. You can't know that, but it's true. So if we take a look at the compiler here, and DemSVC's compiler is kind of bad at SSE style optimization, so it's probably going to be the worst case. It's probably going to be worse than Clang, would be my guess. But if I go ahead and grab this here, and we just go ahead and paste that in, we don't really need an inline here, and we don't really need our weird kind of like boilerplate stuff there that we're using. So I'm just going to go ahead and get rid of that. So if we write this code straight line, I'm pretty sure that it requires me to include in trin.h before it can do anything, but otherwise it should be fine. And let me just see. Let's get this larger. Let me see what else we've got. Float and PS. Got problems. F32. Oh, right. Gotta get that one. Better. U32. And done. Right? Should be. Nope. Okay. So if we take a look at the assembly language that's coming out of this now, which hopefully we should be able to get, you can see that we've got the absolute value routine. Here's what it looks like. Oh, and while we're at it, you know what else we should probably do? Is let's do the other one too. So this is what we were doing before, right? So hopefully we can take a look at what these two routines do, right? I'll label them 1 and 2 so we can see, because I'm just curious like what we were getting before with those absolute values. All right. So if you take a look at what these compile to here, it's not going to be very instructive because these are oh, it looks like we still have something going on. I can't. No, that's right. I just don't know what this little, I don't know what that little orange check mark means. I don't know if that's something bad. But what I was going to say is we don't really have the compiler options in here for optimization. And so we don't really know what it's going to do when it's asked to produce, code that's more usable. So if I just grab like a bunch of stuff here, so at least the thing knows like, we don't need exceptions. We do want inlining. We don't need float consistency, right? So if I just get rid of some of these ones that we don't care about and just focus on some of the optimization ones like this, here's what this will produce, right? So supposedly that's doing the right thing, right? You can see here that, and it's doing with the load. So it's not generating the value, right? For reasons that I could not tell you, yeah, I don't know. So like, and looking at these here, I just don't even know why. Like for some reason, it thinks that it needs to do this load, even though here it knows it can do it. I guess because it's just happens to be FABs. I guess I don't know. But it looking at what it's doing here, for some reason, this dword pointer load, it's doing it as a memory operand, which is the correct thing to do here. And it's not doing it here. It's doing a move aligned and then an and. Now, it's a move aligned, so the compiler even knows that this thing could be a memory operand because it is aligned. So it, because unaligned memory operands fault on non-v prefix instructions. So I'll be honest, I don't really understand why it generated this code. That seems just like bad code gen. Maybe there is a reason for it. I don't know. But, off you go. Because a move followed by an and in that way, it just doesn't make any sense. Like I just don't know. I don't know what the point of that is. Oh, never mind. No. I do see. So for some reason, I see what's going on. It didn't do it because it thinks it needs to load out of RCX the address of this, which is completely nonsensical because this is just, that's just a register. Like that should just be in a register when this routine is called, right? That should just be in XMM, whatever the first pass register is. I don't even remember which one it is, but that should just be in the register. So I have no idea why it would do that. Maybe it's because it can't see the call site. I don't know. So anyway, these all look really good, and what I'm not sure about is, so where are all of these ifs coming from in my code? Is it like a compiler version thing, or like, are we just getting unlucky? Like, because I can go write this code, it's not a big deal, but I'm just not sure I understand why the compiler is outputting all of these if statements. I don't know where they're coming from, right? I just don't understand, because we're getting a bunch of them. We only asked for one if statement, but we're getting 3, right? And so I really just don't know why. So unfortunately, this is not particularly helpful, and I guess, I can't really figure out where that's coming from. I'm going to just go ahead and try then, because I don't know what else to do. If I just, if we look, we say, okay, we're going to come here. We're going to look down here. We see all these compare instructions and all these jumps, jump, 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 right? Let's just see what happens if we replace the absolute value with our other code for absolute value, right? So if I take a look in here and I say, let's just, go ahead and do, this same pattern here, but let's do it in here. In fact, we could even just call this version of the function. I'm not sure that makes a lot of sense, but either way. So suppose we do this and we say, all right, we're going to do the exact same thing, only now instead of doing the and PS with something that got passed in, we're actually going to have to do an convert here, like so. And what we're going to do is we're going to AND with a set one of this thing, right? And also, since this is not wide, these can be set one SS's. I don't remember if that's the intrinsic, though. It may be that you just do an convert. Yeah, I think you just do a convert SS F32. No, convert F32 SS. Convert. I hate the naming scheme. It's just a convert. I just need to convert my float in here, and it's always an adventure of me trying to remember the crazy naming scheme. Okay, so it's not, you don't switch the F32 and the SS, I guess, which doesn't make any sense to me, but okay. Unless it is a set. Oh, you know what would help here? Just give me the vanilla stuff. Oh, so it is so never mind. What am I talking about? It is that, so I don't know. All right, so if we just set these, so we're just basically going to do a set SS instead of a set one, because we only need to set the bottom. We don't need to set them all. And then I'm going to load just this one value here. So I think that should be fine. And now I just want to see, because again, this is the exact same thing. We load the mask, we put the mask into an XMM register, we AND it, so we get rid of the bit, and then we convert, we do convert SSF32 to get the result out, right? So if I actually go back and now look at the assembly language for that, and just say, look, are we still seeing all these all these jumps? And you can see there's actually no jumps now. At least I don't see any. Wait, what's this though? Got like a call in there now? What's the call to? Is the call to this? So now it's doing a call. It stopped welding it in there. And there's still those comparisons. All right, so that was worse. I'm so stumped right now. Where are those comparisons coming from? So then that fabs f was fine. That was not causing any problems. So I guess that's can just remain. And in fact, it seemed to be able to do a better job when it was there, probably just because it's left code and it knows that's an intrinsic for itself, I guess. Because the call is now gone, right? So I don't know. I'm going to start welding this in because I have no idea what it's doing, right? So let's start by putting this piece of code directly into the lighting, right? Because I just, again, I have no idea what it's doing. So since I just don't know, I feel like I need to start inspecting this very carefully. So this here is T, right? And the diffuse atlas in this case is going to be, the octave coefficient. That's going to be coming from the diffuse atlas here, right? Like that. And this R that we've got, the R is going to be what we pass in here, right? So that's the, it's the sample n, right? So take a look at that. And if you take a look at what's going on here, we also don't really need this to be packed anymore because we're loading these out anyway. So we can just, look at them like that, right? So that's pretty straightforward. And I think that, that wouldn't change the behavior of this thing at all, right? So we're not really doing anything weird here. All we're doing is saying, okay, wait, no, that is what we're running, so I don't need that. Yeah. So that's just the same. There's nothing different about that. It's just the same thing as we were running before, but now we've welded it in. Now that should not really change anything, I don't think, because it was already being welded in by the compiler. But every time you change the code, it helps to look, because at this point, right, we have no idea what the compiler's doing. We really don't know why it's making these decisions. That's what I'm trying to figure out. So I just want to test every change I make just to see and make sure that I'm still getting these spurious compares in here. And there is one compare, right? So it makes sense that there'd be one of these if the compiler just did it directly. I just don't understand why there's three, right? Okay, so we've now put that octahedral from unit vector call in directly, and these now should all be pretty straightforward. This is just 3 multiplies. These are just some calls to floor. There's really just not a lot in there. You know what I'm saying? I got to re-up my T. Yeah. So yeah, I don't really know what's going on, but again, I'm just going to continue down this path until I find out. So I'm going to go grab octahedral from unit vector, and I'm going to paste that in directly as well. So now, instead of the UV getting computed by a call, I'm going to ask it to compute the UV directly. And so if this now is going to be UV like so, then I can say, okay, well, R is the thing that's going to get used in here. So previously where we were doing like v.xv, whatever, that's all going to be R's that are, because there isn't a V anymore. And I think that's it, right? UV, 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 UV. And so that's now the code welded together. So now there's no jumps there's no calls that we're asking the compiler to do. So now we've told it to inline everything. Now, presumably, because it was already inlining everything, again, we should still end up with roughly the same code. So I don't expect to see, oh, crap. It's been staring me in the face the entire time. That's where it's coming from. It's this. That's what it is, right? Duh. So here was one test, and here were the other two, there and there. I don't know why I didn't see that, but just didn't. So these functions here, these sinf functions, I think that's really all we needed to look at. I probably didn't need to go through all that, but hey. So these are pretty straightforward, right? You know, I don't know why the compiler wouldn't understand that, but I think it's just because maybe it's a little too subtle for it to suss out. You know, I don't blame it. But it's pretty straightforward for us to just do the same thing we did with absolute value, right? So if we want to take a look at what's going on here in the sign of, all we're trying to do is return 1 or -1, right? And we just want it to match the sign of the input. So what we can do is we could say, look, if we just load up a mask here for this thing, like so, and we assume that the value that's coming in here is the sign that we wanted, and we know that we want 1 to be returned, and we just want to flip the sign one way or the other. That's pretty straightforward. Because if we take whatever the value, if we take just that bit from the value, and then we use 1 as the other value, we can just blend the two together by taking just the 1 bit from the input value and the rest of the bits from the value 1. And merging those together will just give us the answer. So we'd never need to do a test here. There's no reason why we would ever have to do a test here, right? So if we take a look at what's happening, because we're in SSE blah, 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 like 4 point whatever, we should be able to just grab a blend and basically say, look, here's the blend that we're going to do. And what you can do here is you can see how this is working. If the mask is set, it grabs from B. So if it's 1, it's going to grab from this one. If it's 0, it's going to grab from the original, right? So we don't have to use a negation here. And this is why I say, like, really, for more optimal code, like, I feel like if we look at the absolute value code, I feel like the easier thing is just to load the non-knotted value, you know? I mean, it doesn't really matter, but like you can see like sign bit from, you see how this is doing this, right? Like, so it's just better if you do this. And not is a little confusing because I don't remember who gets knotted. So I find it's best to always check. So you see it's A that gets knotted. That's the opposite of my intuition usually. And so, you know, since we want the mask to be knotted, the mask would have to come first. Right? So this will just automatically knot the mask. That way everyone's loading the same value. So it can just store just one value, which is the high bit, right? And it can always just load that same value. So that seems good, right? So when we load this up, you know, we're really just doing the sign bit from here. And we could even have just a thing that does that automatically probably, but it doesn't matter. So I'm going to do a blend V here. I'll load that up again. I'm going to do a blend V here. And since this is wide, I don't think there's an SS version, right? Meaning there's not that. So it's going to do this wide whether we like it or not. And that's fine because we're only going to use the bottom anyway. So whatever. So anyway, we've got our mask and we know that if it's 0 somewhere, it's going to take the lower part. So we want our 1.0 to be what we're taking most of. And then just where that high bit is set, we want our value to be there, right? And that's it. That is the entire sign of operation. That'll just merge those two together, right? And so I think now if we look, we should be getting rid of all of the jumps except for this one here. And we'll take a look at how we could get rid of that jump as well in a second here, because we don't need that one either. So we might as well just eliminate it. Especially because it's not necessarily very predictable. I mean, it might be, but I don't actually know. So there's that one compare. That's this line. And here's the JNB, which this JNB is for the commas, because you can see the flags are not touched, I don't think, anywhere in here. It's just doing the compare, leaving the flags as it's jumping down here, right? So I think, and now you can see these are our two blends. That's where those commas used to be. So I think we're good, right? I think we're all good. So I believe we've still got everything nice and happy here. All of our transmittance seems to be working okay. At some point, we probably need to find some better ways to test this, but we could just see where the light scatters to. For now, it's pretty good. All right. So, given all of that, we might as well just finish what we're doing, because that inspection kind of led down a little bit of a optimization path there. We might as well finish off by just getting rid of these jumps, right? So if we would like to, we can see here that we're doing these absolute value sums here. Those should all be straightforward. Doing the UVs, doing the sinus, all of this stuff can just be done. This is the only part that we don't know how to do yet, and so all we really need to do is use another blend, right? So we know that this would be the condition, this RZ less than 0. Really, this, you can see these two computations, they just compute temporary variables, right? So since these just compute temporary variables, really this is the only thing that's happening in here, right? Like we can just compile this code and it's exactly the same. Because computing these two temporary variables doesn't do anything unless you then assign them anything. So this is really the only part we need. And so if we want to, we can just do like basically a conditional assignment here. And just say, hey, yeah, like UVX equals like, mask assign, something like this. Where we just say, all right, we just need a mask here, and, we'll produce that mask somehow, right? This is what we need to do. Now, it doesn't really make a lot of sense for us to do this in calls, because like all of this should really be done in F32X's soon anyway, because we would want all this to kind of dovetail into our other path here, right? So, I mean, I'm not going to overthink this. I'm just going to say, okay, look, let's make an F32-4X here. That's our Z mask, and that's just going to be equal to that RZ value. So it's just like, look, whatever the RZ value is, if it's less than, do we have a 0 F32X? Yeah. So basically, if RZ is less than 0, then what we want to do is we want to use that to do our blend. I don't know. Yeah, we've got, so it's just this. It's just select. So from there, I can just say, all right, our UVs are going to be selected from that. And then we don't really have a good way of pulling these out yet. And again, I don't really know that we want to, but so temporarily I might just kind of pull them out just to make sure things work okay. But then we can move on. So if we just do a select here, it would look like this. Right, so it is just that mask assign. Right. And then again, the only problem we're going to have now, the only problem that we're going to have now is this stuff is not all in F32X's, right? So like all of these things are not actually F32X's, and we kind of want them to be that, right? Okay. So if you take a look at how these are getting extracted here, Martin's pointed out something that was really smart, and it just was me kind of being a space cadet. So generally speaking, extract is just not a very good idea, right? If you were actually trying to extract an integer value into a general purpose register, then that's what you would want to do. But we don't actually want to do that here in a lot of cases. We just still want a float. So really what we want to be doing is just this always. So we always want extract 0, but we just want to shuff down and put the value we're actually looking for into the low float of the packed version, right? Because there is no x87 code happening here, right? So we're never trying to transit something out of the SSE registers, out of the XMM registers, and put them into the... We're never trying to transit them out and then put them into somewhere else. Like, we're not moving them out of the register store. This is strictly compiler dressing to say, hey, we need to move this down to the first lane just because we know you always generate everything in the first lane. Ideally, you just stay where it was, but there is no way to tell the compiler that. Like, so anytime we downshift from SSE wide to compiler floats, it's too dumb to know like that we might just want to leave it in one lane. And there's some reasons why, at least in the old days, I don't know if it's still true, but there are some reasons why you might not want to do that anyway. The reason is because, at least on the older chips, you'll notice that it's not purely set dressing, even at the lower level. So if you look at like a mul PS, right? You can see that it's generating an actual mul PS assembly mnemonic and instruction. SS is generating something different, right? So it's not actually purely set dressing. You might say, well, what the heck? Like, why is there a mul SS? I mean, it's the register is 4 wide and it takes one, cycle to do it. So 4 cycles to do it. What's the deal? And the answer is, at least in older chips, I know it could save power. Like, it would actually somehow down throttle if all the code was SS code, I think. Right? Whereas PS code has to do the full 4 wide, and I think it requires more power. I think. Do not quote me on that, but I seem to recall something like that. So, if you just take a look at what's going on there, it's pretty clear that that there could be, at least on certain platforms, and I don't know if it's always true, but there could be reasons why you do want that to always be in that first lane, right? For power reasons. So if we take a look at these extract, if this extract code here, we kind of don't want to do this. So I'm gonna leave this here and say change to convert SS. I don't quite want to do it yet, but that's what we're gonna do. I'm gonna do an extract here just because, again, I just want to take this one step at a time. But eventually, what we want to do is kind of collapse all this code down, because we can actually do some of it wide too, right? Like, so there's no reason not to just finish off this routine, right? There's no reason not to do that. All right, so if I go ahead and do an extract 0 here, now we've done all this, in the SSE registers and then transited back, quote unquote, out, but really it would just be staying in lane 0 anyway. And so I think now we should have that entire section of the routine just running with no branch, right? So now if we take a look, we shouldn't see any more jumps in here. It should just be one big straight piece of code, right, that just goes straight on down. And that is exactly what it looks like to me, right? No branchy branch, right? No branchy poos. But again, is this particularly smart? Not really. Because you can kind of see here that we've got some pretty straightforward stuff happening with UV. There's a little bit of a swizzle going on here. So it's not like 100% the same everywhere. But it's pretty close, right? So yeah. So yeah, if we take a look at what actually needs to happen here, it seems like we could probably get some free speed up there as well, just because, what we're doing here doesn't really... What we're doing here, we can just get a few free multiplies in or whatever, like, because some of it's just kind of wide, without really thinking the routine much, like without really overthinking it much. If you look at everything we're doing, I think it's literally all just for the TX/TY computation. Like, there isn't anything else that's happening here. So all we're really doing at that point is saying, well, we can also get rid of this code now. We don't need this. So that'll make it a little easier on us to read as well. There we go. Okay. So now if we take a look at this routine, we should be able to just sort of say, well, okay, where is this stuff actually getting used? So if you look at TX and TY, like, who cares, right? Like, what are those doing and when? So let's take a look at where they actually get used. And what you can see here is really it's just part of the textile pointer thing. You can see it here with the TX, TY stride there. And what you can see is when we actually do this DXZY, you can see the stride Z delta XY bit here. Looking at the strides, it looks like we could probably just add another term in here, right? And then this would just take care of it, right? Where does XY? Was it right here? No, it wouldn't. I take that back because this is specific to this nonsense here. So the base offset, which got computed here. So the term would really, it would go in here. Sorry. So min XYZ times stride XYZ. You could just put a term in here that had these two in it, and then it would just get handled when you did the extraction here. It would extract out those additional terms as well, right? So we probably can slipstream that like really cleanly too, so that top part of the code can be simplified quite a bit, I think. Of course, a lot of this code could probably be simplified as well. But that's sort of a separate issue. Yeah. All right. So anyway, if I take a look at that, let's just see what happens if we start bulking this up a little bit. But keeping these things together seems pretty reasonable because it looks to me like they kind of always end up doing the same thing anyway, right? So those TX, TY values, we can really just flood those out as an F32 4X that just has the X and the Y in it together. And that seems like pretty straightforward, right? At least it seems like that to me. So again, we're going to be sloppy with the loading. We're just not going to be very careful with how things get loaded here. Because I don't know that I really want to start doing any data reorganization or padding stuff or whatever, because I don't know that we really care about that. I don't know how much performance that would really get us. So I'm just trying to get the stupidity out, right? That's really it. I'm not trying to go for like the fastest possible routine or anything. Just trying to get the stupidity out. That's it. So if we take a look at what's going on in here, you can see that we're doing like a divide times an RXY, and there's the one norm here, right? So this summation, there's not a lot we can do there because we're sort of doing a summation, and the horizontal adds are slow, really slow on these chips and not good, and they take the permute port, if I remember correctly. So it's bad. So we probably don't really want to get too fancy with this part, would be my assumption. So we may just want to do like the basic thing that's crappy first. And then, if we really want to someday come and make this routine dramatically better, we can try that as well, but at the moment probably just don't want to go there. So for now, I think I might just do something like this and just call it a day, right? So now we have our UV in here, and we would need one shuffle in order to make this line work out, because now we've got like a thing that's like an OXY, right? And that's going to be this line of code, but unfortunately, as you can see, like this one is right, but this one is the other way around. You know what I'm saying? So we need the two bottom pieces to shuffle around, and so I don't know. We can do maybe this. And there's really no point to the second half of that because we're just shuffling the bottom two PS values around in there, and that's fine. But it always shuffles two vectors at the same time. So I don't know. Yeah, there's really no point to it except that. We could use a shuffle. I hesitate to even bother to bring this up, but so we could use a P shift D here. P shift D would be better, right? And the reason that P shift D would be better is because it doesn't destroy the destination register. If you think about how like this function works, if you look at shift PS, you destroy whichever the register is that you are passing in here, and you can't just pass the thing you want to shuffle here and the other one here because it's lane locked. So flipping the two bottom pieces wouldn't be possible because I believe the two bottom pieces come from the destination, right? I think. Oh no, never mind. No. So it's okay because you could get well, no. No, you can't. So see the destination here, well, it doesn't even say which one's the destination. So I don't know. We'd have to go. This doesn't say, so I'm not sure how to look for that. This doesn't say. But assuming that A is the destination, which I don't know if it is, if A is the destination, you can't do it. If B is the destination, you can, right? So again, because we're not trying to be super smart here, whatevs. But it's definitely the case that, if we were being saucy salamanders about this, then the shuffle stuff, really should just have a big to-do on it that's like some places where we shuffle 4x probably should be using a shuff D instead of a shuff PS because they don't destroy the destination. right? So it's just something to be aware of. Again, I don't want you to have to always overthink stuff like that, because, it's not always important. But it's worth noting, like, if you're actually up against it at some point, right? And you're really trying to optimize some code, because SSE is like an absolutely terrible instruction set, like, it's just absolutely horrid. That horribleness means that being a shrewd optimizer actually does make a difference, because all these like crazy tricks and knowledge about all the specific crazinesses of each instruction do actually end up making a difference. That's not the case on really well-designed instruction sets. The better the instruction set, usually that's not true. So I just thought I'd point out that that's another kind of one of those little weird things where it's like, look, if you really are targeting SSE4, not AVX, because that has V prefix instructions, at which point, it's unclear how much it matters. It's a slight iCache difference maybe, but, who cares? So if you don't have V prefix instructions and, you're really actually trying to get it to go as fast as possible, there are all these little gotchas in there, and you want to be aware of them, because if you really need the performance, there's a bunch of stuff you can think about, right? So, just want to point it out. So that's all. So if we go ahead and do this code as written, then the sign of function needs to get ported to f32x, obviously, which we can do, and then we can get rid of that and just take a look at where the oxy is used. If you take a look at how this piece of code is now functioning, you can see that it's exactly the same. So we can just stop doing the extraction and just let it be exact. Let it be wide. And these are now don't need to be lofted, and the result doesn't need to be extracted, right? So now it just keeps getting a little bit simpler. This now doesn't have to be done as a v2 at all. This can just be the one vector, right? It's 1 plus the uv. And now the UV is correct. So then we get down to here where we've got this particular coefficient needs to be loaded. What are you complaining about here? Oh, 0.5f needs to actually be loaded. You know what? That's probably not going to get used again. So never mind. Okay. So again, yeah, sign of, not a thing that we actually have, but we could have it pretty easily. So if you take a look at sign of, this is the one we want. We already wrote it wide. So if I just go over to, for example, where we had absolute value, which we also wrote wide, and sign bit from, and inverse sign bit from, and blah, 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 blah. All we should have to do here is say, look, we already wrote this wide, so let's just start actually doing that as well. This whole nonsense situation can just stay exactly the same. And this piece here can just do what it was going to do. Instead of doing all of those conversions and stuff, it can just actually do this, just the actual instruction, right? So we still need the set PS here. And the value now, though, is already wide, so that will just work. And I think that's mostly all we need. That's a set 1 PS. And off we go. Okay. So this now has to be fully wide, so that's just a vector of ones instead of 1. The Handmade product here, where we've got the octam coefficient times the UV, that's just going to be a straight multiply, because the Handmade product is just a wide multiply when this becomes wide. So really, this is the only thing that we needed that we don't have, right? And I don't know if we have a loader for V2s. We probably don't. So I'm just going to assume that it looks something like that, and then it can multiply the UV. This here, where it has to load 1.5s in both places, again, is just going to be probably a vector of 1.5s. Nothing particularly fancy there. So it'd be something like this. And, these other lanes can just be 0 for now, right? So that will produce this I value. And to produce our txty values at that point, we just need to floor it. So at that point, we're really talking about this. If you take a look at how this is working, it's producing actual integers. I don't know to what extent we actually want those to be integers. So to be completely honest with you, we may want to leave them as not that at all. Because if you look at what happens through here, we just extract these at the end, but everyone else is just actually F32s the whole way. So I don't think there's any reason to actually force a conversion there. I'm not sure that it would actually do anything for us. We're not working with particularly large values here, so it shouldn't matter. I don't think. And so this txy here, I think we can just do a floor on I and call it a day. So at that point, this is really just a set one. I don't know why I did that. It's really just this. So anyway, at that point, I've got the 2 uses of tx and ty here, which again now, I think I just want to fold that into the base offset because I don't see any reason why I wouldn't. This is just a horizontal add, right? So I think what we can do is in here we'll just say, all right, so the base offset's just going to get the txy value added in, and you can see here that the y part needs to be multiplied by the row stride. You know what I'm saying? So in here, there's like a thing, that looks something like this, where we boost the x and the y. That's backwards though, so it's that, right? Because the y is multiplied by the diffuse tile row stride there. So I think that's the only place the base offset is used. So I think that just works, right? And I don't know that there's anything else we would need to do there. So yeah, that's some code. I probably screwed it up. But that's the actual code in question. What is happening here? All right. So apparently I did screw it up, right? And you can tell that because we're loading out of bounds here. So this somehow, was very unhappy and didn't like anything about its life. And so it decided that it just couldn't go on anymore, somewhere around here. And this is probably not the actual instruction that faulted, because these are broadcast instructions, and you can see that is not what's happening here. This is actually a move unaligned, so it's it's going to be one of these. And so this base xyz value here is probably just wrong, right? Because that's the thing we changed. So if we just take a look and we nerf it, right? Oops. So now, in theory, when we run this, we should end up in a situation where now it's wrong, but it should be, cool. It shouldn't ever fetch out of bounds, right? Because it's just loading one value now forever, right? It's never actually doing offset. So we know that the offset is wrong here. This line looks pretty innocuous. I mean, I could be very wrong about that, but since all this thing was doing before, the only thing that it had to do at all was just multiply the row stride by the y, which it should have done, and multiply the x by just 1, right? It didn't change. So I don't think there should be anything weird about that. Like, I don't think that line should be wrong, famous last words. So I think we're mostly looking at this code up here for whatever the bug is, like whatever's wrong with it, right? Okay. So yeah, yeah. So that looks pretty straightforward, to be completely honest with you. So I'm not sure where exactly that's going strange. Um, that's a little confusing because there's not very much in there. I suppose I should double check the sign of as well, because that is technically part of the stuff we wrote. Taking a look at this here, we're doing a blend V where the mask is doing value P and that, I mean, that looks right to me. I don't see anything weird there. So that seems fine. So I may just have to do step through this to see if there's something weird going on here. The shuffle 4x could also be busted. Let me just see what those are defined to do. Looks pretty reasonable, though. Right. I mean, there's nothing particularly weird there. So I may just step through this real quick to see if I see anything weird going on. And again, I can sort of refer back to this code here and just see if there's anything that I see that's jumping out at me. So if you take a look at the octim coefficient here, which is what this is loading under the diffuse atlas, it's supposed to do that times the UV, which we're assuming we've computed, and that's what it does. It's going to offset it by 1.5, 1.5 on both, which is what this will do. And then it wants to floor that value, which again is what this will do. So, again, not very complicated here. Looking at the UV computation, it's going to be 0.5 times 1 plus the UV. Again, pretty simple. Like, I don't see a lot of weirdness there. So this part just doesn't look that complicated, and maybe I'm overlooking something, right? Like maybe I'm like forehead slapping there a little bit. But so it looks more like this part would be the problem. Of course, that doesn't really make any sense because it seems like that part was already working fine. So I don't know. But this little part here could have been wrong or something. So let's just take a look carefully through it and just see what we can do. So yeah. So taking a look at the octahedral from unit vector part of things. So if we come through this routine here, you can see the absolute value here is just, the sum of these values. And we just didn't, we didn't do anything. Yeah, I mean, we didn't really do anything like that. So that just sums those up. And all the 4 lanes will all have the same value there, right? Because these are all F32-4X replicates. We compute the UV then by doing 1, which is just, 1. By doing 1 over the 1 norm, which is the sum we just did. So that should just be a div PS, right? I mean, I think. Okay. Guess I don't have that in here. No. There we go. So that's just going to be a div, which is what we would expect. And then we're going to multiply it by the r.x, the r.y value, and we're zeroing out the other lanes, right? So again, pretty straightforward. I don't see like I don't know how we screwed that up, but maybe we did. We then have the OXY here, and the OXY value is like the thing that we might use, so we're only going to use it in places where the v is less than 0. But so we want to compute the OXY. The OXY is going to be the sine of x and y, which is what we have, of the UV x and y, which is what we have here, times 1 minus the absolute value of y and x. So that's where this shuffle comes in. It's just trying to reverse the order of those two values, and we can verify that does or doesn't work, because who knows. But it seems like that's fine. Again, I don't see a lot of places where that can go wrong. We then compute the mask here, and the mask is z less than 0, right? And if z is less than 0, then we want to select out lanes of x, y in that particular case, whereas otherwise we just want to leave it untouched. And then we flow into the other routine, right? So again, I don't know. I don't quite see where the problem comes in, because all that seemed pretty good, right? So I'm kind of tempted here, because I don't know. I'm kind of tempted to just call the original code and then look at the two values and see, am I actually getting differences in these values? Or is something else happening here, right? So right about here where we do the floor, I should be able to say like, hey, let's just do a spot check, please. Giving the octahedral offset here for this particular direction, right? And that's all I wanted to do there. Like, I just want it to tell me, like, hey, run the original code path and let me see like what these values are, because they should be basically exact all the time, because we're even flooring at the end. So although maybe there could be occasional places where it's very slightly different because, and then when it gets to the floor, it changes which way it floors. Most of the time, these should actually be like exact. I don't really want to struggle to read these values out, so I'm just going to give it an OD here. So here we are. I'll actually probably put this on the next line there. So let's actually do this. And so now all I want to do is say, look, we've got TXY, and we've got check. And I want to see both these. This is the place where I almost need like George to remind me how the heck this thing works, because I don't remember. So that's weird. I mean, it shouldn't matter because it's going to get handled later, but so that's because of this, right? So we do have things happening in the other two lanes. Is that going to cause a problem later? Because those are the right values, but is that going to cause a problem? It shouldn't, right? Because here's a multiply that should knock out those two lanes. There's the 0, 0 that should knock those out. So why would that shouldn't cause a problem, should it? Well, that's wrong. So yeah, this is just wrong. Okay. Well, good to know, right? So the question is, where is this going wrong? And I have no idea, because it looked pretty good to me. So we're going to have to go through and see where this is going wrong roughly. Since I do have the luxury of doing so, I'm going to do this expansion one more time. because why not? So here on get octahedral offset, I'm going to grab this, and in here I'm actually going to put, I'm actually going to put this in like this, where I can just say, all right, do this computation. Excuse me. Where I've got the direction here. And I just want to go ahead and run this code with the original set of things so I can have the intermediate values. So all I'm going to do is just change these to different names that I can inspect in the watch window. Like so. So that as we come through here, that's all we need, right? Okay. So this is just going to produce all of the intermediate values. And then what I want to do here is probably something like this almost. This is not a very good way to do this, but that's okay. Actually, honestly, we can just do that. Okay. So I think we're good now. And again, there's no point to any of this other than simply that we are trying to compare intermediate values so we can see where this went wrong. So in theory, I should force a fault here, hopefully, whenever these are incorrect. So like that. And so now when we look at these values, we should be able to see that they're wrong. Right, so these are the input values there, and txy check is 4, right? And so now I should just be able to look at the other values to figure out where in the chain we're going wrong, because we're just trying to reproduce a piece of code we already had. So it seems like a waste of time for me to try to hunt the bug myself when I could just run the two pieces of code in parallel and see where they diverge, right? So since I have the luxury of doing that, I'm going to. So let's first look at the check UV. So the check UV values are these. And in fact, we can just look at like the X and the Y here, like so. So those are the check UV X and Y values that we're producing. Those are right after we do this plus bit here, right? So after we do get octahedral from unit vector, which is like this bit here, then we do this, it's this line, right? It's 0.5, 1 plus the UV. So we just want to see what this is. So if we take a look at so those are wrong. Yeah? I mean, that ain't no good. So we've got something wrong happening up here, you know, which means I think since we were doing this, it feels like this is probably must be wrong somehow, right? Like this piece of code is probably busted, this OXY. So that means we got to paste this in and just take a look and verify that. But that's presumably what's wrong. So let's take a look. So if we grab the octahedral from unit vector part of this, and we just shove that in here, like so, this should all be fine. So if we just do these as r's, like so, we were calling this check UV, right? So this is actually going to be called check UV, 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 like that. And this is R in here. Then this should be fine, right? And the problem that we're going to have here is this gets destroyed a little bit. So we probably just want to be able to look at these two values separately. So we might want to do like make this an interim UV that we check differently. So for example, if we did this, now we can look at what the original value of IUV and OXY was, and then what the final value is, so that we know like whether the select is working or something, right? Because otherwise that value gets destroyed, and it's pretty hard for us to know what the heck is going on in here. So if we want to do the same change to this routine, right? All we really need to do is make sure that these are computed outside, for starters, like so. And then we just need to make a new version of this that does both, right? So we would have like this here would be called check IUV, right? So that we have both of those. And then this piece of code here would produce a secondary value. So then we would have check UV equals check IUV. And then this would assign the OXY based on whether it thought it needed to or not, right? So I believe that's all we need. Yeah. And now if we run this, hopefully, again, we can just look up and see what our divergence pattern looks like. So for starters, let's look at check one norm. I don't think this is wrong, but you know, since we now have them, we might as well verify everything. What the heck? Oh, dude. Where did our absolute value go? So, okay, when I just said I don't think this is wrong, that was totally wrong. Where'd our absolute value go? What the hey? That was stupid. That was really dumb. Okay, so now we're reproducing the value. So it was just, we just forgot the absolute value. Happy birthday. All right, so now we should be good to go, I think. And so now we just have straight line sampling there. And we can also take a look at how fast that is, because it's pretty easy for us to do so. How are we doing on... we don't really know how our timings are. It's really very difficult to take them because at this point, this number is dropping quite a bit. And so we're getting down to the point where like debug collation and all this stuff, like if you look at how long these things are taking, this is now like half of our frame time, right? Probably need to fix our debug system someday, but... and so like if you look, you can look at this and it looks like, oh, it's a really high number. This is heavily multi-threaded. So this number is like multiplied by many, right? So the actual frame time it's taking is actually quite a bit less than this. It's going to be that divided by 4, right? So this number is more like the same as that frame display number, right? And you can see that happening in here. Oh, sorry, debuggulation. No, not debuggulation. So just the frame display, just that, right? So waiting on the frame to actually happen is roughly the same amount of time as we're actually spending in here, right? And then of course we've got all this code as well, which, you know, probably is taking too long, but that's sort of a separate issue. So anyway, like, you know, we're getting into good shape here, because as this shrinks down, we're pretty much taking the lighting out of the ray tracing out of the part where it's the slow part of our system, right? So if I go and run, I'm just curious here. So if I do a build, I don't know why I'm in the code directory. That's not what I meant to do. I meant to go to debug and do build HHLightProf, like so. I'm just curious if that affected our runtime positively or negatively, because I'm not sure what it will do, right? You know, we made some changes. We don't know what the effects of the changes are. So I was just curious. I just wanted to, oops, that's not at all what I was trying to do. This is the horror of using two different editors, one at work and one on stream. Oh, God. Life is horrible. All right. So in the lighting system here, if I look at those timings, you can see here's the optimized version here, and that's actually like slower, right? So we're at a point where we're pushing this piece of code, unless I'm wrong about that. We're pushing this piece of code in a certain direction, and that direction may not be good, right? Meaning, because we haven't welded this into the surrounding code, there's just a lot of cruft going on in here, and we kind of need to make sure that we're actually going to do it correctly. Now, also, Visual Studio is a really crappy compiler for SSC code, so it's not going to do us any favors. But we do want to make sure that we can do some of this stuff smart, right? So we've got some issues in here because that's running more slowly than it should be, right? Because if we just left it the way it was, it in theory would have been better. Now, granted, I can't really say why. Doesn't make a lot of sense, but I would like to look real quick to see. Let's see here. In the release build, I would like to look to see what it is generating now for that code. I mean, it looks pretty clean, so I'm not really sure why that would have gotten slower. That's a bit of a mystery to me, to be completely honest. So I'm not entirely sure, but we definitely have some stuff we've got to do, and you know, so I'm just gonna push a little forward on cleaning up this code, and we'll go from there. So. Convert S32 seems fine. Just looking at what we're doing here. So, I mean, really, like, this stuff is not good. And I might just go ahead and fix that really quickly here while we're at it, because I've got these to-dos in here, right? So what I actually want here is I want these all to call extract 0, right? So these are all going to do exactly the same thing. But so all I need to do here is just do a shuffle 4x, right? Where if we're doing extract 1, we just put 1 everywhere, like so. So this is what I actually want to be doing. So for each one of these, you know, it just looks like this. And what we could do is call that a convert F32. So to mirror this, the other thing we could do is say, all right, convert F32 VI, right? And it's just this. right? I think. So then what we could do is anywhere that we were doing extract, you can just do a convert F32 and it'll just pull out the value for you, right? So if we go to like, you know, here, this is convert F32 0, convert F32 1, convert F32 2. What are we complaining about here? That. And then the rest of the places where this was happening, same thing. So this is like convert F32 0, convert F32 1, convert F32 2, blah, 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 blah. Convert F32 0, convert F32. Oh, wait. No, no, no. Not correct. These are all zeros. Okay. And that pulled out one of each. This is just pulling out the 0. So that'd be like this. And to a certain extent, if you're always pulling out 0, you wouldn't need the shuffle, right? So I don't know if the compiler is smart enough to remove the shuffle. So we may need to convert F32 0 as like a special case. You know, I mean, I don't know. So that's kind of a separate issue too. Let's take a look. So, all right, off we go. So that shouldn't change the runtime, I don't think. I guess we'll find out, but that should be basically the same. Oh, so it looks like that was back down to what we expected. Is that just variance that's happening? So we're not slower, we're basically the same speed. Okay, so it looks like there's actually a fair bit of variance in there, actually. I shouldn't have jumped to conclusions. Okay. So if anything, we're actually probably a little faster because it looks like it more consistently gets down lower there. So, okay, whatever. So that's below kind of our noise floor. For this particular test, we don't have a way of really looking at that. So you know, we've seen values that are at least this low, so just be advised. That's where we're sort of at now at our best. So what I kind of wanted to do then is just say, well, what would happen if we just said where we do the compute irradiance? So like here, where we do this compute voxel irradiance at, you know, what if we just went in there and did just that, right? Like, what if we just welded this directly in there so it just falls straight through, and this stuff can just be factored out. And similarly, like this stuff that comes in here can just stay in the registers and doesn't have to do anything, right? So I don't know what will happen there, but I'm just going to try it real quick to see what happens. So if we were to grab like this entire load of crap here, and you can see that reflect color foo, which was already, it's already in exactly the right format. In fact, we can start with that, I suppose. You can see here that this is about to load this thing up exactly the way that it already actually is, right? And the only thing I'm not sure about is when we do the tile loads, we've got to get rid of the 0 lane. I'm sorry, the 3 lane if we want to make sure that's 0. But if I look, it shouldn't matter because it never actually gets used, right? So we nerf that value anyway, so the lane's not actually there. So in theory, this right here can just return this value, right? So in theory, we can say, all right, this is, let me just real quick. So if we pull this out here, and the AABB raycast, which calls this somewhere, like right here, right? So if this thing needs this to be this way, we can just have the wide light sample come back here, and this routine, which is now super slow compared to our new routine, can do the old way. So we can keep both of those running just fine. But now what we'll do is we'll just, for the other case, we'll just return it as an F32 wide so that we're not doing like extractions and then just to weld them back together, right? It doesn't make any sense. So this here will just do an F32 4X. This was just saying reflect color foo. It's already exactly what it needs to be. So we're just going to say, look, here's the reflect level, right? That's what comes back. And we're going to get rid of that. So now we've just got the emission level and the transmission level that happen automatically, and then the reflect level just gets maxed in there, and off we go, right? So I think that should just work fine. It should produce exactly the same results. It's just, again, getting rid of some of the cruft of backing into this slowly from where we were to, slowly optimizing each part. Now you can start to weld those parts together. And, I mean, that's like way more efficient now, right? And again, part of that's just because the Visual Studio compiler sucks at optimizing SSE code. So we're not really optimizing this much. All we're really doing is moving cruft out of it. And moving that cruft out of it is just helping the compiler do an okay job, right? But we haven't done anything. Like all of this has just been kind of just nothing, right? This is all stuff a compiler in theory could do. If it was really fancy. And so all we're doing is just like hand holding the compiler, right? And getting it to the point where it's like, oh, okay, right. I see what you were doing there, right? So that's fine. And maybe this routine can be done a little bit better. I don't know. But if we take a look at what happens on the outside, you can see that we're just doing the max here with this reflect level. This whole thing, right, could just be dropped in here now. So I don't know if we want to do that or not. Like, this may just be stupid. So I don't know. But if I was to just say, all right, dump this whole thing, right? So now reflect level is this. And we're just going to optimize this disaster in place here. So here's this whole giant nonsense factory. And we know that the diffuse atlas code should just work because it's named the same thing. So these things don't have to happen. Probe P single and probe N single are two different things now. So we kind of need to call R probe N single. And these two things, like occlusion D and probe P single, don't get used until down here, right? So there's the sample P. So I'll just name it that to make it easier on us. And then occlusion D isn't even used, is it? Is it? No, it must be. It's the thing that does the occlusion N is what it's called. Okay, so we're just going to start here, which is doing literally nothing. And where's our 1 and 0 here? 1 and 0. There we go. Okay, so again, nothing fancy happening here, nothing even interesting, just welding those things together. And so there's now the final routine, and we can go ahead and run it. I don't really expect it to do anything here particularly much, but you can see like this number just continues to go down, and really, again, there's nothing magic about it. It's just helping the compiler see what the heck is going on. And so, again, if we take a look at where we actually are on this, welding those together more directly, all we did was that. We're now starting to get down towards, we're rapidly descending into where there's very little time spent in the ray tracer at all, right? Because we know that this is a floor. Basically 2.6 is the fastest we could be if we did nothing. If we do no computations, we're at 2.6, right? Do we have any more T action here? Oh, yeah, there's a little bit left. There's a little bit of T left. Okay. So, just looking at the grid Raycaster at that point and saying, should this be welded in or not? I think at least for MSVC's sake, we probably should. And then you can take a look, and these things are already in lanes, so some of this may just be able to persist, and some of it may not. So let's take a look at probe P single, for example, because we don't really know what some of this stuff even does. Because we haven't looked at that part of the routine today even at all. So let's take a look at where that code actually does anything. So that's going to be in the sample P part of the code, right? Which is just this here, right? And so the question is there anything fancy we could do there to prep probe P single in a faster way? I don't see a lot going on there, but, obviously this could be streamlined a bit, I should think. So looking at probe sample P, this is just done completely wide, right? And if you look at what's going on there, it's only doing it just to do this, right? So if we wanted to, actually, we could just add this and have it be in the right place to begin with, right? Also, what the crap is going on here? So here's what I'll say. I don't know that I want to do it now, so let's maybe wait till tomorrow to do this. So let's go to Q&A now, but I'm just going to say, look, now we can streamline this code pretty significantly, because we can make this stuff just line up with what it actually needs to be on the way out and save a bunch of shuffling, right? Take some pressure off of port 5, which I think is the only port on Skylake that can do anything shuffle related. So let's just say, because now I think, now that we know that we're just going to leave these in XYZs. We're not trying to do this multiple at a time. So we're only going to get a 3x speed up ever on this stuff. We're not going to get 4x. And so just that's the way it is. We gave up on that because we don't really want to do the machinations that might be necessary to get that happen. So we're not going to do that, but we want to just get this flowing smoothly with that 3 wideness, because there's a lot of opportunities for us to take advantage of that. So we're just going to do that. Right? And it won't be the world's most optimal Raycaster, but it's pretty darn good, and it's getting faster and faster and faster, so I'm pretty happy with it, right? So I think that's all we really need there. And so let's just go to a brief Q&A, and then tomorrow we'll just pick up right back where we are. You know. Sorry to be off topic. I finished all the 5 days in the intro to C, and it was awesome, but there's a huge gap between the intro and the main course that I'm not able to fully understand. What's your suggestion? I'm new to programming, started reading K&R recently. I don't have a suggestion at the immediate moment. The only thing I can say is I do have a C course coming up. So I'm trying to address this. There's going to be a C course coming up. You can put your name into Star Code Galaxy to sign up for when it's ready, and that's a complete course. Basically, it will take you from knowing nothing. So like the idea is it takes you from any number of points. So knowing no coding, knowing coding but not C, knowing C but not low level, or knowing low level. And from any of those points takes you to complete game implementation. So it should do what you need. Unfortunately, it's not quite ready yet. I'm trying to get it out soon. It's just I just have so much stuff to do. It's hard for me to always. Yeah, there's too much stuff to do in the world, unfortunately, and so and not very many people are ever doing any of it. So that's just where we're at. But yeah, the intro to C stuff was just a thing that I tried for test streaming to see how things would go. But then it turned out tons of people use it because there's so little good intro to C stuff. So I've been asked for the past 5 years of Handmade Hero all the time, like, how do I learn this base stuff? And I'm like, I don't know, because the learning materials are all terrible. So I'm trying to rectify that. So hopefully, eventually, starcodegalaxy.com for if you missed it. Starcodegalaxy.com. If you just go to starcodegalaxy.com and sign up there, that'll be, well, I'll send it out, and then folks can have an option. We haven't announced like pricing or availability and that stuff, but I think it'll be around $50, so it'll be pretty cheap, and it'll come with everything. So that's the current plan. I don't know what the actual release plan will be, but it shouldn't be. It's not going to be one of these like $10,000 coding boot camp nonsense things. It'll be very affordable. All good? All right. Well, I guess if people have questions that they haven't thought of or posted here, they can always ask them tomorrow, because we'll be picking up right here where we are leaving off. So I will go ahead and close it down. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you want to follow the series at home, you can always pre-order the source code, pre-order the game, rather, and it comes with the source code. So you can follow along at home. That's on handmadehero.org. I'll be back here tomorrow to do the rest of that routine, just get that slipstreamed and nice and clean. So there's not all these weird extraneous shuffles. Hope to see you back here for that. Till then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.